Okay, thank you again to be here for the lecture of today. Look at this picture. As I told you, this part of the course is dedicated to the, let me say, control or control systems of some controllers which are used in automation. Look at this example here, which we have seen last time. Isn't a robot. If you look at this picture here, it seems a really complex robot, in which you can imagine that we can have different freedoms of the degree of freedoms. We say this means I can consider different joints. We can consider also in particular these joints here, which could be and rotational joints, could be in translational joints. I didn't tell you about that because this is more connected with robotics. But what I told you last time, I considered just one degree of freedom. What is the meaning of degree of freedom? Yeah, I don't want to go in depth. Last time, I told you very quickly. Basically, it means that I can have just let me say, roughly speaking, one movement. No? This means I move just vertically the system. The degree of freedoms characterize also, let me see, characterize also the, how possible to say, the number of states. About the states, I told you a lot in the dynamical system. I mean, each degree of freedom is characterized by two states. We have seen also here, no? We have seen that we have position and velocity. No? This means this allows to say if having an articulated system with many degree of freedoms, we have two times, excuse me, the degree of freedoms states. This means basically what I told you last time, the application in this example of transfer function. About the transfer function, I told you during the presentation. The transfer function basically characterizes the system in terms of input-output. You remember last time in the presentation, I told you that in some books you find the notation or the nomenclature external representation. About that, I already told you a little bit in dynamical systems. External representation means it's basically connected with the forced answer. With the forced answer. I don't know if you remember. We have this connected in the sense that reflects the forced answer, but in S domain, just to repeat a little bit, the Laplace transform, as I told you last time, which characterize again the external behavior, which is connected, we reflect the forced answer. Forced answer we have seen in dynamical system. Again, we have just one degree of freedom. This means I am moving just vertically, up and down, up and down. The rest is fixed. Image that the joints, you understand the joints, no? I don't know in German what is. What is joints? Gelenke, yeah. We have just one Gelenk, active. Is the Gelenk which, it doesn't matter which one. It doesn't matter which one. But move up and down. This means we have just two states, as I told you, because we have just one freedom, degree of freedom. X, Z and Z dot are the state. I don't want to repeat that. We know better than me from dynamical system. Model. Also the model we have seen in dynamical system. Very important here, the concept is not only, let me say, the structure, basically the structure of the robot, in this case, is almost irrelevant, because is relevant if I have a more than degree of freedom, believe me. But we have one degree of freedom. Basically, everything is connected, or mostly is connected with the model of the object which I have to quit, which I have to crash, let me say. I don't want to crash. To fix, let me say, in production system, we say to fix. Even though this M here, this mass, represent not only the mass of the object, but also the mass is the moving mass, everything, considering robots and object. Of course, it's extremely abstract because I don't distinguish between the mass of the object and the mass of the robots. If we want to do that, this is really a little bit more complicated, really more complicated, even though remain with one degree of freedom. But remain with the time which we have, remain on this context here. We have just one mass. Of course, isn't a simplification. Isn't a simplification. Not only, do you remember, I told you that I am considering the mass concentrated in one point. About the concentrated masses or concentrated parameters, I don't know if you remember, I told you a lot in dynamical system because it's the topic of the dynamical system. Like here, no? Where is this elasticity and damping characteristics concentrated? Typically, in this object here, it's not concentrated in one point, it's distributed. But try to abstract, otherwise it's extremely complex. Typically, this is the topic of PhD program, in which we have a partial differential equations. We didn't, also in dynamical system, I didn't tell you of partial differential equation. Partial differential equations model, excuse me, the distribution of the characteristics of the system. It's not the topic of bachelor's, typically also is not the topic of master. This is the topic of PhD program, really advanced modeling, which very often is also difficult to find. Yeah, I don't want to difficult to find application, but for instance, in robotics, we can find something similar in the flexible joints, which you cannot consider this para-elasticity concentrated in one point of the robot. But this is a little bit too far away from our lecture. Let me go ahead. But in any way, I tell you this because so we have a little bit the feeling, also the limitation of our analysis. In any case, look, we have this model here. We have seen in dynamical system in different situations. Yeah, two states I already told you. I skip a little bit. Very important here, these two effects which characterize the movement, the spring force effect and the friction force effect. You remember this equation here is an equation we have seen in the context of dynamical system, and the second order linear system or the linear equation with concentrated parameters. About concentrated parameters, I told you a lot also today, let me say, in which also Ks and B and beta don't have an extension. It's just in one point. This means no dimensions. If I apply the Laplace transform on this equality, probably it's better to reconsider this. No? To remember again, we have the energy, this reflect the energy which we have in the system. If I apply the Laplace on the left and on the right, and if I consider the derivative theorem applied twice, do you remember? I told you very quickly, it's typical, nevertheless. I told you just how I can calculate, or it's the theorem, the derivative theorem. This means the Laplace transform of the derivative of the function. You remember? But if I have the second derivative, I didn't demonstrate it. It does not exist in the theorem. There is a corollario in which we say apply twice this theorem. We have that the second derivative of a function, if I have to do the Laplace transform of the second derivative of the function, this equals s squared multiply the Laplace transform of the function. It's exactly what I'm doing here. And the unit thing, which I didn't clarify explicitly, but I told you when I introduced the theorem, the derivative theorem. The rest is known. We can see here the derivative, the first derivative of a variable. But please pay attention. This Laplace transform is a formal transform or a transformation. We can see that using the property which I demonstrate or partially demonstrate, we can transform this differential equation, which could be also difficult. For us, probably not, because in dynamical system, I insisted a lot. But we have many advantages because we have a compact representation without considering any knowledge about the solution of differential equations. You learned me, Benedict. No, we repeat it together. Probably we did in dynamical system in more physical meaning, I would like to say, with more physical meanings. We compact really this representation input-output, which reflect the forced approach or part of the answer. In particular, allows to calculate the transfer function. Do you remember the transfer function is defined as the transformation of the output divided the input. For instance, if the input here is the force, typically in this representation, we have the force, we reflect the energy which I put in an input, and the output could be the position, could be the velocity, could be the reaction force, could be anything, could be the acceleration, everything which you like. Could be also just the spring force, could be also just the damping force, everything which you can localize, let me say, as an output in this equation could be considered as the numerator of the transfer function. Just repeating quickly what we did. And if you remember from this equation here, I can really calculate very quickly the transfer function because through algebraic calculation, I can obtain this, which somehow, or at least the denominator of this transfer function, reflects our differential equation, because our differential equation was m multiplied z dot dot, I don't know if you remember, plus beta multiplied z dot plus ks multiplied zeta equals f of t. But somehow we can see that, of course, we lose here the physical meaning because we are in an imaginary domain, the S domain. But everything was, until now, calculated formally, basically using some theorems, but we use just algebraic consideration. And then you remember, in the same way we calculated the transfer function between velocity and force, we can see that the denominator does not change. Very important. I told you last time, the same denominator changed just the numerator. Interesting, Somehow it's intuitive to understand because if you look at these two transfer functions, the transfer function 2 and the transfer function 1, they have the same denominator, but this different numerator. Very important to understand. The numerator changes, but doesn't change the denominator. F is here, F is here. And this is reflected in the fact that the denominator of the transfer function remains the same, but change the numerator. This S here reflect what? Reflect that the velocity is the derivative of the position. Also, this is clear. And is reflected by the derivative theorem. The derivative theorem says that the Laplace transform of the derivative function is S multiplied the Laplace transform of the function. Is exactly what I did here. What I did here to calculate very quickly, if you want, the new transfer function, the transfer function G2, because we know that S multiplied Z of S is exactly V. If you remember the derivative theory, it's difficult. Now, it's difficult? No, no. I'm going too fast, probably, the repetition. If you remember the derivative theory, it's here. The Laplace transform of a function which is derivated is S multiplied of the function without derivative, because in S doesn't make sense to derivate. And we don't have, no? This is the theory. We have seen with a function f, here we have a function z. It doesn't matter how I, which notation I use. Z isn't a function, it's the position. It's a function of the time. Remember, in the theorem, I wrote f of t, because the mathematicians use f of t. In our case, in order to represent this vertical movement, I use z, but I can use f. It's just a nomenclature, a new nomenclature. Z is our f of t. Will change over time. Is this difficult? This is easy. This means using again this really fundamental theorem, the derivative theory, which can be also used for the second, the third, and so on. Applying this, I can directly calculate this transfer function. This was the question, because it is enough to apply exactly the theorem of the derivative, because S multiplied Z equal V. S multiplied Z capitalized, to be precise, equals V capitalized. This means if I multiply my original, my G1 by S numerator and denominator, I didn't change anything. You see, because I cannot. I have nevertheless here, this numerator here, I can call this numerator, let me take something to write. I can call the numerator V, because the equality S multiplied Z of S equals V of S. And now, if I have to calculate V divided F of S, V divided F of S is enough to multiply by S. Here we have it, V divided S. But I can write, instead of V divided S multiply F of S, I can write in this form. I don't know if this is, I multiply basically S in the numerator and in the denominator, excuse me, left and right. Think about this. Here we have a 1, here we have a V of S, right? If I multiply left and right by S, I have this one. Is visible? Again, here, try to image V of S because of this equality, which came from the derivative theory, right? Try to image here V of S. We have a V of S divided S multiplied F of S. But if I multiply now left and right, this equality by S, I cancel this S here, and I have an S here. Should I do the calculations? Okay, please stop me if it's too difficult or is unclear, so I can clarify. Yeah. Zoom in. This is a little bit more. I have just an auto zoom. I don't think so. It's a little bit more in focus, but I don't think so that we can zoom in the sense, in the strictly sense. I try to clarify this if it's not clear. Because this question here is always in the examination. In which sense? Build a model, which is know from the dynamical system, and calculate the transfer functions. This is always the. If for you is clear this expression, assuming that this is clear, I think this, I repeat it enough. No? This S is an appendix, is not a variable. S is an appendix, it's not a variable. Now, look at this. Did you agree on this? Clear, no? I didn't change anything. I multiplied by S here, I divided by S here. I didn't change anything. This means I can say that this is equal to the same. You remember in high school, no, or in elementary school, I can multiply numerator and denominator for the same entity, for the same thing. I don't change anything. This means I have right to write equals this, which is this one. I didn't change anything. I just formally multiply by S numerator and denominator. Look, but what is this? Is exactly what I'm looking for. Because V of S is S multiplied set of S. Why that? Because I called V the velocity, and zeta is the position. But this allows me to apply the derivative theorem, because the velocity is the derivative of the position. This we learn many times also in, I don't know. This means that implies something like that. Clear, no? Now, let me write again this. So at the end, you cannot say that I didn't explain. At this moment, I didn't change anything. This expression here can be written in this form. Please say to me if you agree what I'm writing. Did you agree with this expression, that this expression here is equivalent to this one? What I did, I multiply left and right by S. We did always this in high school. No, we have an equality. This is an equality. I can multiply left and right from the same thing. Too difficult? No. I think this is elementary school. No, but we have seen many times. No, but it's okay to repeat. I remember when I was in Santa Barbara, I did my PhD in America. My professor says to me, please don't be shy in the sense, write also the basic knowledge. No? Now, what I can do here, did you agree? I can cancel S with S. This was the original. Until here, I clarify. Conclusion. This is the transfer function G2. We called this G2. In a second transfer function, which I can see in the system. I can see many transfer functions. Try to do at home. Otherwise, I try to do here for you. The transfer function acceleration force, acceleration divided. If you want, I can do for you. So we do, but this is immediate. Did you agree with this? In which the denominator, please pay attention, is always the same, reflects the fact that f of s remains in G2 and in G1. G2 is V divided F. G1 was Z divided F. We can see that we preserve the denominator, change just the numerator. Why that? Because in the transfer function, we have another numerator. I try to help you also to build quickly, immediately, to build quickly the transfer function. In the exam, you have to show me the calculation, but you know the results somehow. You can calculate in 1 second. Tama. I understand what I intended. Typically, we don't say so, but the message is clear. It's not wrong what you say, but formally it's not correct because we don't have the derivative, or at least in derivative in time, if you think of derivative in time, in S domain. Because when you use S domain, you lose the time. Now, if for derivative you intend the derivative theorem, we can understand what it's correct somehow, or at least help to calculate. In this sense, now I ask you, what is the function G4? Because G3 we call the reaction force divided force last time. Let me say G4, let me say is, I think G3 was, we called last time, or I didn't call. Okay, I didn't call. It doesn't matter. Let me write G4. Now, in accordance with what you told me, in your opinion, what is the transfer function between acceleration force, or in some books you find between force and acceleration, but in any case, is acceleration divided force. In accordance with what you told me, it could be a good idea in mind, but I don't want to write in a publication but it's clear what I intend. It's clear. You can say, or you can have in mind this concept. Now you have to tell me about this transfer function directly without doing many calculations. What is the acceleration? You won't directly write the transfer function? The acceleration is the derivative of the velocity. We applied once exactly what you told me, that we did somehow the derivative of the. This means, in your opinion, what is this? The denominator is the same because we have the same force. The denominator, this denominator, the explicit denominator, if the formal denominator does not change, if you have the same force, remain the same, we can demonstrate, but I have seen once. What I have to write here in your opinion? Yeah. With the concept which you told me before, even though I don't want to write in, because we don't understand formally, but conceptually, yes. I don't know if you agree this. Think about 1 second. But I apply again the derivative theorem. This guy, you can say, I can write also in the publication. But I don't want to write that we derivate the transfer function because, but you understand what intent. This is a good, yeah, exactly so. We assume that at this moment, we have no initial conditions. You remember last time, now I will repeat this. I told you in case we have an initial condition, for an easy example, I considered a relative easy example, what changes? Thank you, Tamo, for remembering me. Yeah. This is an assumption. Otherwise, we have to add something. The calculation is a little bit more complex. I showed you in order to understand conceptually for an RC circuit, right? Last time. You remember? I will upload never tells everything in my study. I will show you again because this is extremely important because at the beginning I told you that this reflects the forced answer. Do you remember? And in the dynamical system, the forced answer was calculated for initial condition 0. In general, nevertheless, I can use the Laplace approach also for the free answer. It's a little bit more complex. And then I will repeat it shortly. Yeah, in this sense, I am assuming that the initial conditions for the position, for the velocity, are 0. Otherwise, having to add something. We will see again in an easy example. Otherwise, here is a little bit, let me say, boring too. It's not difficult, but we have to consider the initial condition. Now everything is clear. Let me write here 2b. Excuse me, I wrote something in the wrong. And then, very interesting. I concluded last time. Yeah, you are right, Tamo. No? In general, you can use also the Laplace transform to obtain the total answer. No? But typically we don't use. Typically we used for the fourth answer. The reason is in automation. In automation, very often we are working in steady state. In control system, we are considering both. Therefore, dynamical system is closer to control system because you remember I consider both transient and steady state. Here in automation, very often, or at least the focus of automation is more steady state. Therefore, I told you just it is possible. I considered just an easy example to show you that this is possible. But here, of course, we have to consider twice initial condition for velocity, position, and velocity to calculate everything. Now, extremely. It's not extremely, but in the production system, very often it is important to calculate the reaction force in order to, if I want to squeeze this object, but let me say fix this object. The very important thing is don't destroy the object. To maintain fixed without destroying it. This means very often we are interested to calculate the reaction force. F R of S is the Laplace transform of the reaction force, which is defined, or we can define in this form. We can see here. In this form means that is the forces of in general the force which the object acts on the robot. Or let me say again, the force of the robot, to be precise. I don't know if this could be understood. It's a possible definition. What is this FR? Is the force which the object acts or the works against the force of the robot. Let me say, roughly speaking, against the robot, even though it's not clear, no? Because the force against the robot is the force against the force which the robot try to apply to the object. Did you agree? Minus because it's up. Look, this is, you are better than me, of course, but let me repeat again. The positive direction, remember in, I don't know, in math or with Bene, the positive direction of this movement zeta is down. Hmm? You can put, which, it doesn't matter which positive direction. But I put so because typically you can do as you want, but this is more intuitive because I fix in this direction. This, I move 1 centimeter down, positive, because yeah, typically we consider the same direction, but it's intuitive. I don't need to explain. Now, the reaction force is minus because it's up in accordance with this positive direction of the position and of the force. Yeah, now, if I reconsider the Laplace transform of my dynamics, if I consider now the Laplace transform of this reaction force, we can combine these two expressions. And what we have is this expression of z. Let me clarify a little bit better. First of all, let's consider again this expression here, which can be written here inside. This I mean, I can plug in, but before plugging in, I have here f of l, because from here this is plus f of l. Yeah, if you consider this expression, I have this expression. This means if you look again of this expression here, you can write z of s in this form, no? Because it's enough to put in evidence z of s. And then I have to divide by this element here, which here multiplied z of s. Is this clear? Or do I have to? No, this is clear. No? I put in evidence z of s. We have this expression here, which multiplied z of s here on the right. This means z of s is minus f of l, if you consider this expression here, divided this beta s plus ks. Is this difficult from here to here? No. This is the Laplace transform of my reaction force, which is defined here. This is the definition. Definition means, please, this is because it's so. Huh? Then I will reconsider the dynamics. I do the Laplace transform of my reaction force. Just looking at the reaction force, I can calculate Zs. Z of s. Is clear this? This expression is the result or came from this. Yeah, can write here Fr equals Zs, which multiply beta s minus Ks. Should I do it? This is easier than before, no? If it's not clear, I do it for you. It's clear. Put in evidence Z of s. I have a Z of s, parenthesis, This means which multiply beta multiply S minus Ks parentheses. Here. And then I can calculate Z of S. If, here, excuse me, I didn't see. It's already here, excuse me, it's already here, the clarification. Probably some students the past semester asked me to write this. It could be. No, it's clear. It's writing. I will upload everything. But if you notice something wrong, now again, if I consider this is written. If I plug in 3, if this set I plug in it, why that? I have to eliminate set. Because the idea is to calculate FR divided F. It's clear that I have to eliminate, etc. Disturbing me because the goal is here. Please calculate the transfer function defined by FR divided F. What is the meaning? I have an input Fs of the, or that, yeah, Fs, we can say so, of the robot. What happens on the object? The goal of this analysis is to monitor what is the output. The output is always the numerator. The goal is to monitor what happens in the object in terms of force. If you exceed some value of FR, the object is broken down. For instance, it could be a possible application. I mean, at least conceptually, it works as a possible application. It's not exactly the dynamics of the system, how fast velocity or acceleration, but more something related to the structure. Yeah, you can say in this sense. I try to tell you a little bit the goal. Yeah, and then let me. If you consider this expression here, because we can see from 3 that we are close to obtain an equation in which appear just f of s and fr of s. We have to eliminate this. But using this expression here, I can eliminate. I can plug in this expression here. And probably we can see that was set of s before, no? With minus, of course. This was set of s. I have to consider minus because I have this. Now I explained a little bit better in the sense more in detail than last time. Huh? Too fast? I'm going too fast. But I will upload. But it's good if you write something because help you. Now we need the last slide. Yeah. Again, the idea. This is basically our original equation, in which I put just fr of s, which I defined here. Yeah, ideas means it's in the definition. I defined everything which against against the force of the robot in this form. Here is clear now. Huh? Just to the definition. If this is clear, as I told you, it came from the Laplace transform, from the definition, from the Laplace transform of the definition of the reaction force. If this is clear, and this is clear, it came from this. Now, this was the original dynamics. Always think of the dynamics, which is the main equation. What disturbed me here it's z of s. Why these two? Because my goal is to calculate fr divided f. The goal is to look at the reaction of the object when I have an input and a force input. This means this is enough now to plug in this in this equation. This in this equation. Excuse me, this. In fact, you can see minus, instead of z of s, you have exactly this expression, which we calculated using the reaction force definition of beta, the Laplace transform of the reaction force definition. And we have this. Now, here we have everything which we need, Fr and Fs. The rest is exactly what we want to obtain in terms of input divided output. In fact, you can reconsider again this expression here. I copied just to for my is more comfortable. Here I move, let me say so, this on the left. From here to here, I move Fr on the left. So I have on the left everything which is related to Fr. I can move this on the left. Then I can put this in evidence. But of course, before put it in evidence, I multiply by the denominator of this. I don't know if you can recognize what I did from here to here. From here to here, if you consider this numerator divided this denominator, I have exactly what I have here. Because I have this multiply Fr minus Fr. I don't know how I can displace this, but if you want, I can do the calculations. From here to here, I don't know if it's clear what I did. I put in a common denominator. This means I multiply this element here by beta multiply s plus ks, and I divide it by beta multiply s plus ks, this element here. And then I put in evidence. Should I do it? That was clear, huh? I put here the common denominator. Is that clear, huh? From here to here. If you multiply this by bet s plus ks, and I divided this by bet s plus ks, I didn't change anything. I can always multiply numerator and denominator for the same thing. And then I put in evidence Fr between this and bet s plus ks. And I have this. Should I do? I think this is math in high school. Huh? If you want, I can calculate for you. Huh? And then we are ready, because I can consider Fr divided Fs. Fr divided Fs from this equation here is this expression. Here is not an S variable, is S pedix. Ne? This is S pedix. Ne? It seems to be S variable, but it's S pedix. Think about otherwise I can calculate for you. It's difficult for you from here to here, right? Again, from here to here is difficult. Everybody? From here to here. What I did, I multiply this element and I divide this element for this coefficient here. Coefficient, this expression, this binomial expression, yeah.
Das ist, wenn man aus dem Buch FR rauszieht.
Ja, auch.
Hier mit FR.
Then we have -1, ne? In the parentheses. You put in evidence directly here. Fs, which multiply m minus m s squared divided this -1. Everything multiply fr. You can do also so. ms squared divided this denominator -1, everything multiply fr. You can do also. But look, again, please pay attention. The denominator is always the same. Why that? Because fs is always the same in G1, in G2, G3, G4. We introduced today also the acceleration. What is the numerator? Yeah, the numerator reflects as before the transformation of the numerator, which we are considering. You remember we had in the position the parameter, the coefficient 1, in the velocity s, because velocity is the derivative of the position. We have, when we are considering the acceleration, the numerator, the transfer function between force and acceleration, we have s squared. Why that? Because s squared is the second derivative, or reflect the second derivative of the position. Here we have something more complex, but it's exactly the expression of the force in terms of Laplace transform in accordance with what we defined. But basically, also before, the velocity is exactly, if I write S, is exactly the Laplace transform of the velocities, if you want, with respect to the position. Here it's quite similar because we have a combination. Why as this expression? Because this reaction force, we defined the reaction force as a combination of two variables, position and velocity. If you read, if you look again this, how we define the reaction force as a combination of two effects, linear combination of two effects, velocity, which you can find here, and position, which you can find here. You have now the possibility, if you think about it a bit at home, to write directly the transfer function. If you do some exercises in electrical system, mechanical system, because it's not so difficult, because we defined the reaction force as a linear combination of the effects of the velocity through beta and the position to ks. I don't know, think about that. It's extremely, if you reread at home how we calculate the first transfer function, Z over Fs. How we calculate the second transfer function, V over Fs. And this transfer function here is extremely easy to calculate the transfer function. Few minutes, I will repeat a little bit also what Tamo asked me. Is it okay here? Very important, the denominator does not change if the denominator in the transfer function don't change. F is always the same. Of course, if I consider a different input, and this means a different model, because you remember in dynamical system, before modeling, we orient the system. We define the input and we define the output. Now, the output can change Of course, can change also the input. But if you change the input, change structurally the model. Example, with Andreas. If you have an inputted voltage, yeah, this is the example. The system, the representation of the system is not the same if you have an input current. Also here, if you consider, instead of the force mechanical, you can consider the status pressure. The pressure in this sense, it depends. Anyway, another input, of course, change structurally the model. If you have the same input, but different output inside the dynamics, of course, the denominator remain the same, but change the numerator. We have seen this example. Typically, it's all what we need, because if you have a transistor, you can consider the input as the current. If you have a battery or a voltage generator, we have a voltage as an input. And the output could be different because you can consider to monitor or to control more than one output for a given input. This is a little bit the way to proceed. Let me in these 10 minutes answer again the question of Tamo, or to repeat what we did last time, in case we have initial conditions. Again, in the analysis of the when we use the transfer function, please remember, don't forget this analysis. Please don't forget this analysis is valid in case the system is linear or linearized. I hope that to go more in depth with the linearization, because we worked here also in my lab with linearized system. This is also a topic of control, and in automation we are working in S. But to work in S, if the system is not linear, this is not possible. Please pay attention. These analysis, these results are valid just if the system is linear. You can ask me, but you told us that the linearity is an abstraction. The linearity is a simplification. It is. Not always. Sometimes reflects the reality, but we can also linearize the system. About the linearization, it could be that this semester I tell you a little bit more than I am not sure. We will see how you react. But it could be, it makes sense to tell you a little bit more about the linearization method. Look, this is the last slide, and we have to move for the seminar. You can stay here, no? Remember this example? I think it was this example, no? Yeah. Here I clarify a little bit the model of the switch with the sigma. In the lecture, in the table, we don't find the sigma because the sigma is engineering idea, how we can model a switch when we start the simulation. For mathematician, the simulation does not exist, at least at that time when they build this table. But just to simulate the switch, sigma is something which is one starting from zero, no? Larger or equal to zero. This balance is clear. Kirchhoff balance of this system here, matter. No? U input is equal U on R plus UC. UC is the state, if you remember, dynamical system. Now, R is the voltage UR, the voltage of R, is R multiplied the current. But what is the current? It's C multiplied the derivative of UC. You remember, in dynamical system, we have to build everything as a function of input states. This here. Then I do the Laplace as before. I will upload. And if I give you, for instance, in a step with amplitude 1, you remember the table, we have the Laplace of this 1 multiplied sigma, 1 multiplies 1 divided S. And the Laplace of this is this one. But plus, please pay attention here. I put also this element here, assuming that the capacitor is not empty. Do you remember when I presented the theorem, the Laplace theorem, which is, the derivative theorem, I presented with f of 0 equals 0, do you remember? But I told you, if I is not 0, I have to consider minus f of 0. You have to keep in mind, don't learn the theory, but keep in mind, in the exam, I don't ask this, but you have to know in case you will work in your bachelor thesis or a project with me, and we will see a little bit later some possible application. But now you can understand that this expression here is a little bit different, because if you C of 0 is 0, is exactly what we did in the mechanical system, which we considered Z of 0 equals 0, V of 0 equals 0. Now, from here to here is just the Laplace algebraic calculation. Here could be 0 if no voltage at the initial. Yeah, and now from here, I can calculate VC of S, which I put in evidence here. Just basically doing some calculation. I don't know from here to here if it's clear, but basically we can say I multiply by S everything. I multiply by S everything, and then I divide it by this. Once multiplied by S, I divide it by S multiply this expression here. If I multiply by S, I have an S here. And then when I divide it, of course, this will change. It's a little bit, the clarification is here. I mean, it's, yeah, something like that. This expression here is an alternative way, this here, an alternative of this. Also, this is an alternative of this. I don't know if it's a little bit difficult, too fast from here to here, probably. I don't know. From here to here. Last time I tried to clarify, it's algebra. It's just algebra. I didn't apply any concept. Probably could be easy if I cancel this. This means I cancel this, I will have this. This is clear. VC of S is 1 divided S multiply this. Of course, if I have this, I have to do similar calculations. But anyway, it seems to be a little bit complicated because I have to multiply by S everything. And then I have to divide by S, multiply this element between the parentheses. And this S is S simplified because I have an S. This S here is after the multiplication. Is this difficult, this algebra here? No. And then I can use the table in Beck form, and then I can transform using the table. Beck, what is this? And what is this? In order to show you this, the idea was exactly your question. That I can use nevertheless Laplace for both free and fourth answer. But typically we use just the fourth answer, at least in automation, because in automation is not exactly control system very often. Yeah, what is important for us is what happens independently of the initial condition, independently of the free answer, because very often, yeah, we are considering the automation. When I say steady state is not correct, no, because steady state includes also the free answer. No? When the free answer, how possible to say the steady state, the final answer of the total answer. But anyway, we neglect the contribution, let me say, so it's precise, with the contribution of the free answer. We consider just the fourth answer. Okay, I stop now recording. I pause the recording.